Slide 1. This presentation will outline the fundamentals of quantum entanglement. It will be assumed that you know the basics of bracket notation. Also, material from the previous presentation on the density operator will be used. If you have any questions, comments, or suggestions, please leave them in the comment section below. If you ever need more time to look at the slide, pause the video. Slide 2. When two or more particles are entangled, then measurements are correlated between those particles. That is to say, two particles exhibit quantum entanglement when one depends on the state of the other. For example, suppose that two particles, A and B, are generated so that their combined spin is known to be 0. If we measure the spin of particle A and find that it is spin up, then the spin of particle B must be spin down, as the measurement would show. Conversely, if the spin of particle B was measured and found to be spin up, then the spin of particle A would have to be spin down. Therefore, some interpreted entanglement as evidence of a paradoxical faster-than-light communication of information. Einstein, Podolsky and Rosen published a paper in which they criticized quantum mechanics as incomplete because of this perceived defect. However, these views are based on the premise of local realism, the principle which has been largely refuted by experiments demonstrating Bell's inequality. Slide 3. The tensor product of two vector spaces V and W is denoted as follows. If V has dimension P and W has dimension Q, then the tensor product has dimension PQ. The tensor product of two matrices A and B can be given by the Kronecker product. It consists of a block matrix of elements of the first matrix multiplying the second matrix. If A has dimension M by N and B has dimension P by Q, then the tensor product of A and B will have dimension M by PQ. Slide 4. When an operator A acts on a vector V in the vector space V and an operator B acts on a vector W in a vector space W, then the tensor product of the operators acting on the tensor product of the vectors is the tensor product of the vectors obtained with each operator acting on its respective vector as shown. Also, the inner product of a tensor product of two vectors is obtained by multiplying the inner product of each vector. Various notation can be used for an element of the tensor product of two vector spaces. We will mostly use the second and third forms. However, any of these forms should be understood to represent the same tensor product, so that they may be used interchangeably. Slide 5. The notion of quantum entanglement can be given the mathematical basis. Suppose that there are two non-interacting systems A and B in Hilbert spaces AICHJ and AICHB. The tensor product will represent the Hilbert space of the composite system. An entangled state will be a non-separable state of this composite system. To say that a state is non-separable is to say that there are no vectors Cj of A and Ck of B such that their product is Cjk, the coefficients of the state. The Bell states are separable states. One Bell state is shown. Notice that for a given state of system A only one possible state of system B is represented. This is the essence of entanglement. Knowing the state of one system, either A or B, will yield the state of a second, entangled system definitively. Slide 6. Let systems A and B be elements of the Hilbert spaces AICHJ and AICHB, respectively. And let side be an element of the tensor product of spaces A and B. The density operator ρ is given by the outer product. The partial trace of ρ over the basis of system B is given by the summation shown with the density operator and the elements of system B. This partial trace yields a reduced density matrix. The reduced density matrix can also be obtained from the full density matrix by adding diagonally the adjacent elements of the matrix as shown. Slide 7. An entangled Bell state and a pure state is given. Compute the full density matrix and the reduced density matrix for them both. Compute the probability that each system is in state 0-1. What is the probability of a measurement of state 1 in B given the state 0 in A in both cases? Please pause the presentation here if you wish to further review the question. Slide 8. We will sometimes omit the tensor product symbol, and denote the tensor product by juxtaposition of the vectors from the two spaces, as was shown in the notation in a previous slide. Starting with the first system, we find its density operator in outer product notation. Please pause this video in order to further review the information presented. Slide 9. We manipulate the density operator in order to simplify all calculations. First, We reverse the order of the bra in order to make the density operator easier to read. We then move the bra and ket for system B to the outside in order to simplify our calculations. The partial trace of the density operator with the basis of system B is performed in order to yield a reduced density operator which is shown with the subscript A. Please pause the video here in order to further review the slide. Slide 10. We perform similar steps to find the density operator for the second system. First we start by writing out the state of the system in terms of the vector elements of the tensor product of Hilbert spaces A and B. We then use the notation of adjacent bras, omitting the tensor product symbol, in order to simplify our notation. Slide 11. We then compute the density operator using outer product notation. The expression has many terms, but is rather straightforward to compute. Please pause the video if you need to review this slide. Slide 12. The partial trace is computed with the basis elements of system B. The resulting reduced density operator is noted with a subscript A. It is given here in outer product notation. Please pause this slide for additional time. However, the operation is relatively simple to perform if you look at the expanded form of the density operator on the previous slide. Slide 13. The basis for the tensor product space of the two Hilbert spaces A and B is shown. We use these elements to form the density matrix as shown. The density matrix is covered in another video tutorial on the density operator, which can be found on this channel. We can see that the bras changed along the columns, while the kets changed along the rows. Please pause the slide here if you require additional time for review. Slide 14. All of our effort has led to this point. We can calculate the full density matrix from the density operator. The results are shown for both systems 1 and 2. The reduced density matrices are computed from the full density matrices. They could have also been easily computed from the partial trace if so desired. Please pause the slide here if you need to review the data. Slide 15. The computation of the probability of finding the system in a certain state can be done through the density operator or looking at the density matrix. We see that the probability that psi1 is in state 01 is 50%. We also see that the probability that psi2 is in state 01 is 25%. The probability that system B is in state 1 given that system A is in state 0 for psi1 is 100%. This is because the two states are entangled. This fact is evident from looking at the state equation for psi1. The probability that system B is in state 1 given that system A is in state 0 for psi2 is 50%. This can also be seen from the state equation. We can use Bayes' theorem to derive these probabilities. This calculation is omitted here. Slide 16. Entropy can be used as a measure of quantum entanglement. The higher the entropy, the higher the entanglement. The maximally entangled state will have a maximum entropy of 1. The pure state which is not entangled will have an entropy of 0. Slide 17. In this problem, we must calculate the entropy for a given state. We see that one possible state is missing from the state equation. This gives us an indication that there may be entanglement. Please pause the presentation at any time if you need additional time to review the material. Slide 18. We first find the density operator. It is found in outer product form from the state by using distributivity. The process is identical to the one we used in the previous problem. Please pause the slide here if you need time to review. Slide 19. This allowed us to construct the density matrix. The form of a density matrix is shown for a bipartite system of A and B. The results of the calculation are shown. Pause the video here if you need to review the material. Slide 20. From the full density matrix, we construct the reduced density matrix. It is also possible to construct the reduced density matrix from the density operator. The reduced density matrix yields eigenvalues which we use to find the entropy. The procedure for finding the eigenvalues from the matrix is shown. Pause the video here if you need to review the material. Slide 21. Solving the quadratic formula from the determinant gives us our eigenvalues. After we have found the eigenvalues, we can insert them into the formula for entropy. We sum over the two eigenvalues that we found for the reduced density matrix. The answer we get is about 1/2. We can loosely state that the state is about half entangled. Slide 22, the Bell states are for maximally entangled quantum states of 2 qubits. A qubit is a quantum bit of information. Here the 2 qubits are represented by the systems A and B. It is said that the Bell states are the simplest examples of quantum entanglement. The Bell states were used by John S. Bell in his description of the Bell inequality. You are encouraged to further investigate Bell's inequality in the context of Bell's theorem in order to see how it showed a violation of the principle of local realism in quantum mechanics.